All right. So last time we talked about black body radiation. We talked about Einstein and the photoelectric effect and how he ushered in the quantum era. So now we know that light is quantized, and the energy of an individual photon of light, an individual piece of light, particle of light, is based on the frequency. Now, what we're looking at here is the emission spectrum for hydrogen. Each one of these is a series of lines. Okay, that if you were to if you run electrical energy through hydrogen, it will emit light, but it will only emit these specific frequencies or wavelengths of light. Okay. This here is the visible spectrum, and if you have a spectrometer, then you could actually look through it and you would see a series of lines from a red line down here to looks like a yellow orange. Sorry, not yellow orange. Actually, yellow green, and then all the way up into blue, and progressively harder to see blue violet lines. And each of these is a series that was explored by a different scientist. So there's the Balmer series and the Lyman series, and others. I don't recall what the alphas are, and I don't particularly care. So what everyone was doing was they were trying to explain the source of these discrete lines. Why is it that hydrogen will emit light at these wavelengths and not at any others? That's what a fella named Rydberg was studying. And he looked, again, yes, ooh, isn't it pretty? This is the Balmer series, the visible light series. From red way over here to light blue, and then progressively harder to see shades of blue. And this is Balmer's formula explaining the series for his particular set of lines. So the wavelength of light is equal to B, just a constant. And then you have these numbers. N is an integer, so 1, 2, or actually, no, in this case, it has to be greater than 2s. So 3, 4, 5, 6, and so on. I mean, he didn't have any sort of explanation for why this worked for explaining the lines that show up here in the visible spectrum. It just does. So this guy named Rydberg realized that he could generalize Balmer's formula and remove the 2. And just have 2 different integers, n1 and n2. And thus, 1 over lambda it's called the wave number. It's kind of like frequency. This is the Rydberg constant. Again, it's just a number to make the math work out. And then 1 over n1 squared and 1 over n2 squared. And all that matters is that n2 is greater than n1. So you could have 2 and 1, 3 and 1, 3 and 2, 4 and 3, anything like that. And when you use this formula that Rydberg used, you will not just get Balmer's series, you will get all of these. Okay? So that was a pretty big deal, a pretty big breakthrough. But the question people immediately came up with is, why the hell would the hydrogen atom care about numbers? It's an atom, not a dork. It's not a geek, right? So why would it care about integers? So let's step to the side and go to the Bohr model of the atom. He said that the reason that hydrogen is emitting integers of light, sort of like that, is because electrons can only exist at specific orbits. Okay, so here is the hydrogen nucleus with its 1 proton. Here is the first orbit of the electron, and the 1 electron in the hydrogen atom. Here's the second orbit. So what happens is a photon of light comes in and hits the hydrogen atom, and the electron absorbs the energy that's coming in. It doesn't have to be a photon, it could be any sort of energy, and it jumps up to this higher energy level from n equals 1 to n equals 2. So it goes from its ground state, where it's happy, it's relaxed, to an excited state where it's high energy. Then sometime later, it will release that energy in the form of a photon of light. And because these two orbits are always the same, that photon of light will always be the same, and it will always have the same energy. And as you'll recall from Einstein's understanding of Planck's work, E equals h nu. Same energy means the same frequency or the same wavelength every single time, so it's only going to release a particular wavelength of light. And that's why you get all of these series. Okay, this one down here is for n equals 1. Electrons jumping back down to, or falling back down to, I should say, the lowest energy level. This is for n equals 2. Electrons falling from a higher energy level down to the second energy level. This is for n equals 3. Electrons falling down to the third, and so on. This is energy level 4. This dark blue is energy level 4. This green is energy level 5, and this light blue is for energy level 6. Okay, so that was Bohr's explanation. But it sort of left open the question, why can an electron only exist at particular orbits? Why can't the electron exist at half an orbit, or 3/2, or 4/3, or something like that? Why only at this particular distance from the nucleus? Okay. So our next clever guy, I left him in there, mostly because I really like his full name. Louis Victor Pierre Raymond le 7e Duc de Broglie. We just call him de Broglie, mostly. Dead white guy number 14, if you've been keeping track. He said, okay, if light can be like a particle with a photon of light carrying energy, maybe particles can be like energy. That is to say, maybe particles can have wavelengths. Maybe your particle, when it's moving, maybe it actually has some sort of wavelength. Okay? And that would explain why it can only exist at a certain radius, at a certain distance from the nucleus. Okay, because the distance, the radius, tells you about the circumference of the circle here. So closer in, you'll have a shorter circumference. Further out, you'll have a longer circumference. So if your electron has a certain wavelength, then sometimes that wavelength will match up with itself and the electron can exist there. And in this case, you see it doesn't. So if the wavelength doesn't constructively interfere with itself, if it doesn't overlap nicely, then the electron just doesn't exist at that orbit. But if it does, then you get these really pretty, overlapping, reconstructing wavelengths, okay? And that's n equals 1, n equals 2, n equals 3, n equals 4, n equals 5. Okay? And that would be an explanation for, or could be, he hadn't confirmed it, right? It could be an explanation for why electrons can only exist at certain wavelengths and not at any others. Okay? And he came up with the math for that. And he found that if a quantum mechanical object has a wavelength, then it's equal to, there's Planck's constant again, h over the momentum of the particle. Okay? Momentum for classical physics is just mass times velocity. A heavy object moving at slow speed might have more momentum than a fast object with not much mass, a light and fast object. But for a quantum mechanical and a relativistic object, in the 20th century era of physics, you have to take into account the speed of light and things like that. So this is the formula for the de Broglie wavelength of an object. And you could do that for any object. You can do it for a thrown baseball. But the wavelength of a fastball is so ridiculously small that it's not even bother worth looking at it, because the mass of a baseball is massive compared to an electron. It's ridiculously huge. So the wavelength is super, super tiny. But if you have a very small object like an electron, then the mass is really, really small, so you can get an actual wavelength worth looking at. Okay? Or at least that's what de Broglie predicted, and that is what we actually observe. I know you're thinking this is awful, but you're not going to have to actually do math with this guy. I'm just showing it to you so that we can sort of look at the math, get some sort of physical understanding, hopefully, and then forget all about it. Okay. Like I said, this is what we actually observe. You remember the double slits of waves, a wave passing through a wall with two slits cut in it, making an interference pattern? You could do that with electrons. And that is exactly what you see. You see an interference pattern with electrons passing through a pair of slits. The electrons are interfering with one another, and they're making a wave pattern. So in quantum mechanics, they have what is known as wave-particle duality. Let me write that out. Wave-particle duality. Okay? Just meaning that particles can be waves, and waves can be particles. So that is the insight we get into the nature of things like electrons. That's by looking at the de Broglie wavelength, the de Broglie's math. Okay. So this is where things are going to start getting super duper weird. Our next dead white guy, that was Erwin Schrodinger. He said, okay, what if we have a particle in a box? And what we're looking at here is technically an infinitely deep well. Okay, V, this capital V, is a symbol, or the letter that's often used by physicists to talk about potential energy. So the potential energy in this area is equal to 0. The potential energy outside that area is equal to infinity. So it's like being at the bottom of an infinitely deep well. Or you can just call it a particle in a box, because anything you put in there cannot get out. It's impossible, because they'd have to have an infinite amount of energy. So anything there is equal to, is just stuck there. So he thought, okay, what if I were a particle in a box? How would I behave? Well, he had some constraints on the behavior of the particle, because the probability of finding the particle anywhere in the box has to be 100%. The probability of finding it right here at x equals 0 has to be 0, because it can't climb that infinitely high wall. Finding it here at L has to be 0, because it can't climb this infinitely high wall. So he played around and he looked at different mathematical formulas. You can get a number of mathematical formulas that work for that. Okay. So, for example, a parabola, x times x minus L, right? Because I know my parabola is drawn really crappily, but if x equals 0, then the whole thing equals 0, so it goes through 0 right there. And if x equals L, then it goes through 0 right over there. You make it negative so that it flips upside down, so you have a positive probability of finding it down there. And that's one of the ways you can do super duper awesome math. It's just making stuff up like that. But that's not the actual energy of a particle in a box. Okay, there's no way to actually predict the energy of a particle in a box. The formula for finding a particle in a box, I should say, the probability. You just have to go out and look at a particle in a box and find it. And this is what we eventually found. This, again, god-awful mathematical formula. But it's actually a lot better than it looks. Okay. This right here is the energy of the particle in the box. There's Planck's constant again, h. In this case, it's actually h bar, which is just h over 2 pi. Take into account the fact that we're looking at circles and things like that. And this is n, energy levels again. N equals, in this case, an integer, 0, 1, 2, 3. The ground state, the first excited state, the second excited state, energy levels going up and up and up. Pi squared, that's just a constant. Then 2m. I think we're looking at the formula for an actual electron here. Just the mass of the particle. That's what it is. Okay, the mass of the particle. And L is just the size of the box we're looking at. That's it. Hold on while I turn off my timer. I'll finish with this slide, and that'll be it for this lecture. All right, and this is the probability of finding a particle at any particular location x inside a box. This is just 2 over L. It's just a constant to normalize it so that the probability of finding it anywhere is equal to 1. And then a sine wave gives you, it's a wave looking like that when you graph it. No, let me go back there. Okay, sine wave, looks like this, when you graph it. Okay. And then n pi over L times x. That gives you, for x equals 0, sine of 0 is 0, and sine of pi, or 2 pi, or 3 pi, or 4 pi is going to be equal to 0. So whenever x equals L, it's going to be equal to 0. And then you have n. That's where the n actually comes from. I should have started with this. The n, it comes right out of this fact that the way to actually describe a particle in a box is using a sine wave, because you can have an infinite number of solutions for a sine function, I should say. And then n is just describing the energy of the particle. Higher values for n give you higher energy levels for the particle in a box. Okay? So this is what they look like. Here is your infinitely deep well. Here's n equals 0. Here's n equals 1. N equals 1, n equals 2, n equals 3, and so on. It's just, the sine wave gets more and more compressed as the particle gets higher and higher energy. All right, so that is, I didn't have to draw it. Those are the energy levels of our particle. And this is what happens when you look at an electron in 3 dimensions. And because an electron is in 3 dimensions and it has not just mass but charge and things like that, things get a lot more complicated. But don't worry, you're not going to have to concern yourself with this function either. I'm showing it to you because I'm mean. Okay. And that is where we're going to stop for the moment. We're going to end with a particle in a box, and we'll come back in our next lecture, and we'll look at the actual electronic structure of the hydrogen atom.